Question 8 had four expressions involving exponents and basically rules for dealing with exponents, or some of the observations that we've made with how to simplify expressions with exponents. One of the key things that we've talked about in class is that when we simplify things, that means that if we have factors of any particular base, we need to collect all those within one spot, right? So we don't want to have a to the third and then somewhere else in the expression an a to the fifth, right? So these are all just a collection of factors. We want to group them together. And the other thing is that we don't like to see negative exponents for historical reasons. It's not that we can't compute with them now, but negative exponents we like to avoid. So this first expression, you look at it and probably many of you wrote down the answer was a to the ninth. I'm reluctant to say it because it's wrong, and I don't want you to lock that in. The thinking here is, just look at it. There are 7 factors of a squared, and if I was to write them out, there's 1, 2, 3, 4, 5, 6, 7. That's a lot. 1, 2, 3, 4, 5, 6, 7 factors of a squared. Every single one of these contains 2 factors of a, right? Each one of these, because it's a squared, it's an a, etc. Well, if I expand that out, there are a total of 14 factors of a here, right? That's why we write this as a to the 14th power. So the observation is if I have a power raised to a power, I can simplify this by multiplying these 2 exponents, right? I can raise this a to the second to the 7th by just multiplying 2 times 7 and recording that there are 14 factors of a. So this is the correct answer for a, and of course you recorded it in this box over here. If I look at B, dealing with negative exponents, I think we're getting to a point where we are more comfortable with just manipulating them and not thinking about why it's true. But if we go back to the y, if I want to destroy this negative exponent, my only tool really is to multiply this denominator by x to the 4th. Now, of course, I've just radically changed this expression because I multiplied just this denominator by x to the 4th. If I want to preserve the value of 3 over x to the negative 4th, I could also multiply the numerator by x to the 4th. And the thinking there is that I'm really just multiplying by the number 1, so I'm not changing the value of my original expression. It still contains all the same information, and it'll evaluate the same regardless of the value of x. My denominator, if I look at it, simplifies to x to the 0 power, which simplifies to just the number 1. So I've got a 1 in my denominator. No longer does it contain a negative exponent. There's no x to the negative 4th. And my numerator is pretty straightforward, right? It's just 3x to the 4th power. So the answer that you probably should record is just 3x to the 4th power. Now, if you make the observation, there appears to be this thing going on that if you have, for example, if I had like a to the negative 2nd power over 2, I could simplify this by simply moving those 2 factors of a down into the denominator and recording it as 2 over a squared, and that would be correct. If I had 1 over a to the negative 1st power, that's equivalent to just plain old a to the 1st if you want, but it's just a. So there's something going on here when you move negative exponents across the vinculum, this fraction bar. The sign changes. Provided that we're looking at only factors, there's no terms at all. Of course, it's not magic. It's just based on the fact that I can multiply by a special value, a special version of the number 1, and just transform this. So let's look at part C. C has it has this 2x squared to the 3rd power. So one of the things I've noticed some of you are starting to do is if you don't see exponents within an expression, I notice that you're starting to go ahead and write those in. So if I look at this, there's 3 factors of 2x squared. So literally that this part right here is a 2x squared times a 2x squared times a 2x squared. That simplifies as 2 to the 3rd power times x to the 6th power. So I'm going to just leave that there for a moment. The other thing I'm going to do is I'm going to move these 2 factors, right? That's y to the negative 2nd. I'm just going to bring up here and make it y to the positive 2nd power, and recognize there's now a factor of 1 left behind in the denominator. And then over here I've got this y cubed over 8. So bringing these things together, if I look at the y squared times y to the 3rd, that's y to the 5th power. So I'm going to rewrite this as, and in fact this is the number 8. That's 2 times 2 is 4 times another 2 is 8. So I'm going to rewrite this as 8, and then I've got my x to the 6th power, and I have y to the 5th power. That's 2 factors of y and 2 more factors of y, all over 8. And you can see there's a giant 1 here, right? 8 divided by 8 is equal to 1. So the answer you should record is, you could change the order, but x to the 6th, y to the 5th, and equally valid would be y to the 5th times x to the 6th because of the commutative property of multiplication. For question D, this seems slightly more straightforward. I'm squaring 3y squared, so if I raise each of those to the 2nd power, that's going to become a 3 squared times a 2 times 2 is y to the 4th power. Then I've got times a factor of x. And I'm going to conveniently move these 3 factors, this y to the negative 3rd, and that's the same as 1 over y to the 3rd power. You can see there is a giant 1 here. I can clean it up to make that a little bit more obvious, but 3 squared is 9, and I can rewrite this as y to the 3rd times y. So if you look closely, what I'm saying is that y to the 4th power is clearly the same thing as y to the 3rd times y. And the reason why I wrote that is because in my denominator I have a y cubed, and I can clearly see here is a giant 1. So those are common factors that I can eliminate. So I'm left with in my numerator 9 times y times x, and I did sneak this factor of x over here. So 9yx or 9xy is the simplified version of that expression.